Hi, everybody. We are back, and we're going to continue our discussion. In previous segments, we talked about support vector machines and a little bit of introductory look at neural networks. In this segment, we are going to focus on wrapping up a brief discussion of classification and regression trees. We're going to see how those are used as really a submodel of random forest, which is another very powerful classification algorithm that can also be applied to regression problems. And then we're going to take a little bit of a detour and we're going to talk about just some clustering algorithms, which are a type of unsupervised learning technique. And we've talked a little bit about unsupervised learning in prior segments of the course. And here we'll take a little bit of a look at clustering. We haven't used a lot of that, but it's good to be aware of what they are. So let's talk about classification and regression trees, the CART model here. So CART produces a very nice visual tool to use in prediction, to use in forecasting of an output class from a feature set. And that visualization is known as a dendrogram. Okay, and if you are great with vocabulary, then you might remember, hey, that's something associated with a tree. And that's exactly what the CART algorithm does, is it essentially takes your variables and it creates a binary tree diagram by splitting these variables up into really child nodes. And it does this by kind of recursively subsetting the original data set and looking at the importance of different variables in predicting the output. So this model is using a binary split of a node to create two child nodes for an independent variable based on that variable's importance in predicting an output. So here is an example where we have two pieces of input data. We have the height of an individual and we have their weight. Okay, and the output that is trying to be forecasted here is whether or not the individual is male or female. Okay, and you'll notice in this dendrogram, right, we have these two variables, and in each variable we have a split given a particular condition on that variable. So if the height is greater than 180 centimeters, meaning if you are sufficiently tall, and the answer is yes, then the model is going to predict here that you are a male with 98% probability. Okay, otherwise, if you answer no, then we go to the next important variable, which is weight. And then we ask, well, are you sufficiently heavy? You're not tall, but are you sufficiently heavy? And if the answer again is yes, then based on this data, you will be a male with 89% probability. However, if you answer no, meaning you are not very tall and you're not very heavy, then the prediction is you're going to be female, and that will happen here 11% of the time. Okay, so this is the idea behind a classification tree, right? It's essentially a calibrated binary decision tree to help you predict that final outcome. Now, the next type of algorithm we're going to look at is something called a random forest. And if you're wondering what's the obsession with nature and trees today, well, we talked a little bit about biological structure as an inspiration for some modeling tactics. And a random forest also falls into that class. These are extremely useful in classification and prediction problems. They also can apply to continuous problems like regression, where you're predicting that continuous unbounded, potentially unbounded output. And random forests are very similar to CARTs. However, instead of using all of the training data, what the random forest algorithm does is it actually samples subsets of that training data, right? Very similar to how we use some cross-validation techniques to randomly sample subsets of data to use to think about building the model. So they are similar to CARTs, okay, but the random forests are using a subset of data, and they use that data to build a CART. So if you're wondering, well, what's the difference? Well, the cart is one tree, but the random forest will keep resampling over and over again with replacement from the training set to create multiple versions of that training set. Okay, sometimes I'll refer to this resampling technique as related to something called bootstrapping. So the idea here is we'll start with the training set, and then we'll resample from that. We'll put all the observations in a bag, draw them randomly, stick them, record them, put them back, redraw again, and we'll be able to generate multiple sets of samples. And from each of those different samples, right, because there's a little bit of sampling error every time we resample from our original data set, okay, we're going to wind up building slightly different versions of the cart. So the random forest, it contains many different carts. Each cart is estimated by resampling slightly different sets of observations from the original training data. Okay, so we're essentially dealing here with a hierarchy of multiple dendrograms. Okay, that's what we're looking at. We have a bunch of different dendrograms. It's not really a hierarchy, but they are horizontally oriented. So not so much like a neural network where you have predictions feeding into new nodes, new predictions. Okay, but here we have a bunch of different trees planted horizontally. You can imagine that is our forest. And each tree, okay, if we have a new prediction and we want to classify it, what we do is we put that new prediction in every one of those trees. So maybe we have 1,000 trees in the forest. We put the new prediction in every one. And you might be wondering, well, each tree may give a different prediction because they're built from different data, and that will happen. But the idea is if you resample enough, okay, then you will have enough trees that give you a consensus of what the right class will be, incorporating some elements of randomization there. So what we're going to do at the end here is once we put the observation through each tree in the forest, we're going to look at the classification that's predicted by every tree, and then we're going to use a democratic voting process. Okay, we're going to vote for the observation, or rather for the class that shows up most frequently, that is predicted by most of the trees. So the big picture of random forest here diagrammatically looks like the following, right? We have our data set, and we resample that data set. And every time we resample that data set, okay, we're generating a new data set and a new tree, right? So in this situation, it looks like our forest has 4 different trees here. Okay. And we can take an observation, we can put it in each tree. So we take the same observation, goes in tree 1, same one goes in tree 2, same one goes in tree 3, same one goes in tree 4. And we will look at what all of the trees are predicting. So we see tree number 1 said it belongs to class C, tree number 2 says class D, tree number 3 says class B, and tree number 4 says class C. So you'll notice we got 2 class C's here, which means our prediction based off of the majority voting in the final class would be to choose class C. Okay, so that is the idea behind a random forest, and I'll show you in a later segment how to implement that in a software package. Let's shift gears a little bit to unsupervised learning, clustering. Clustering is a very useful unsupervised learning technique. It only really uses input data in order to associate different classes. And classes may not be what the user expects them to be a priority, because the computer algorithm has no information on the output classes. The patterns that might be uncovered may differ dramatically from what is expected by a person. So we looked at this clustering example that I had borrowed from a colleague before. This was the situation where we were putting different coins into a vending machine, right? Really old school machine learning here. And the 2 important features to identify the coin were the size of the coin and the mass of the coin. So this was an unsupervised learning picture. Note that we can sort of see clusters emerging here, and it looks like there's a group of things together up here. Okay, there's a group over here. And then it looks like maybe a group here. and a group down here. And this is maybe a little easy to see in 2 dimensions, but you can imagine you could have a hyperdimensional data set where you have 1,000 features. And then, it's really difficult to just look at a diagram in 2 dimensions and identify clusters if you have 1,000 features. So this is a clustering application here that we're thinking about, right? We can't, in the unsupervised framework, we cannot see the labels of those points. We just see, hey, there are a bunch that have the same set of features, very similar features. So this isn't the first time we looked at this example, but here was the actual supervised data perspective, right? We had these different clusters of the 10s there are dimes, 1s are pennies, 5s are nickels, and 25s are quarters. Up there on the top right, the biggest and the most massive. So this is essentially what we mean by clustering as an unsupervised learning algorithm. It's looking at the data and seeing, without really knowing what output class you're predicting, just what things are similar. Okay, and it starts to group them together. There are many types of clustering algorithms. We're going to just talk about a few here. So one of the most basic and still commonly, widely used is something called k-means clustering. And with k-means clustering, the way it works, and we're going to take a look at this, a few iterations of the algorithm in a moment, but the user specifies the number of clusters, k, and then the algorithm fits the data into the best groups as possible, given the number of clusters specified by the user. This method scales poorly computationally, meaning it's not, it's okay for big data, but time to convergence and complexity can be an issue, as n gets very, very large. Not as bad as hierarchical clustering, which we'll talk about momentarily. But this is used pretty frequently for big data applications. As I mentioned, if you have higher dimensionality than just 2 of your inputs, then it's really hard to just eyeball a visualization and tell. So it's good to be able to do this. The key feature of k-means clustering that you should really be aware of is this first one. The user specifies the number of clusters. How would the user really know what the number of clusters are, though? Right, that's the big catch-22 here. Okay, so that's a weakness of that algorithm. Now, there's an improvement on the k-means clustering called x-means clustering. So just one letter switching in the name there. And the improvement here, hopefully, is what you guessed. X-means clustering basically repeats the k-means procedure, not just for one k that's user specified, but it loops that process over and over to check for the optimal k. It identifies the optimal number of clusters, meaning it doesn't require a priori a user to specify what they believe the right number of clusters to be. And this is also, really good and used very, very frequently in big data apps. Last type of clustering we're going to talk about very briefly is hierarchical clustering, which builds clusters incrementally by assigning each observation to its own cluster, and then combines similar clusters at each stage of iteration. It also does not require the user to specify a cluster, which is, again, a big benefit over clustering in the form of k-means. However, it tends to scale poorly in big data applications. So I'll show you just a visual representation of hierarchical clustering, at least one type of hierarchical clustering. There are 2 types. There's a bottom down and a top up, one where you start all the observations in one group, then you break them apart. And then another one where you start them each separately and then you join them together. But we'll come back to that visually momentarily. But let's take a look at k-means clustering in action here. Okay, and what we are looking at here is some data. We have 2 dimensions, a dimension 1, x1, and a dimension 2 along the vertical axis here. And it's maybe a little hard to see, but it looks like we have 3 x's in this diagram. And those x's mark what's called the centroid. center of the clusters. There's one here associated with the green cluster. There's an X hiding underneath those data points there associated with the blue cluster. And there's an X over here associated with a red cluster. Now, the other thing that you should be able to see here, and it's again a little hard, is that the data are colored according to which cluster the observations are closest to. So you can imagine picking any data point. Right? Let's, for example, take a look at this data point right over here. Look at that data point, and we could measure the shortest distance to each cluster. 1, 2, 3. And then the computer does the math and says, hey, you know, it's a little Pythagorean there, but the computer identifies, hey, this is actually the closest cluster, so we're going to label you that same color. So that is how this works, right? So notice all those ones that are colored red are closest to that red center, that red X. All the ones that are colored blue are closest to that blue centroid, and all the ones that are colored green are closest to that green centroid. And we can think about an error measure here, right? What do we want to do? Well, we want to move the centers of those clusters in a way that makes the distance from the data points they're associated with as small as possible on average. That's kind of the way we want to think about this. So you'll notice this green center over here, okay, is very far from these data points that have the same classification, right? Really, really far from those. So that's creating a lot of error in the cost function. So by moving that centroid over to the right, we could reduce a lot of error on those points. And at the same time, though, you're like, well, what about these points here? We're going to induce some error on those points. And you might be right. But remember, they may now be closer to the blue centroid, and they would be reclassified and then not affect the error relative to our movement of the green centroid. Okay, so what we're going to think about here is moving not just the green centroid or the blue centroid, but we're going to think about moving all of them in iterations by checking those distance conditions. Okay, so here is one such iteration. Boom. Okay, here's initialization, iteration 1, initialization. There's our first iteration. Okay, so what happened? Well, you'll notice that green centroid did as we predicted. Right, moved a little bit to the right. Moved a little to the right. The blue centroid moved a little bit up and to the left. Or sorry, the green centroid moved to the left. Got my left and my right confused there. Looking at the mirror view here. Blue centroid moved up and to the left. Here we can see that. And then the red centroid moved up and to the right just a little bit. So it looks like we had a kind of a counterclockwise motion of all those centroids here in this first iteration. So the red one moved up. That's what we saw here in iteration 1. Okay, now notice the other thing that happened here is that some of the blue points are now reclassified, right? These are blue points here that used to be green points. And then some of the old blue points are now newly classified as red. So all in the red class here. And note our green class, we still have some of these. And we still have all of these ones down and to the left. So it looks like still we have a lot of error from the green and the blue classes here. The red maybe looks like it's more or less centered. So let's take a look at the next iteration here. The next iteration moves us. Let me just clear those circles. So next iteration moves us here. Okay, so that green centroid, what happened to it? Moved down and to the left. The blue centroid moves a little bit further up and to the left. And the red centroid had a tiny bit of motion. Tiny bit of motion there. But that was what we were observing in the last iteration here, which I'm saying up at the top is convergence. So suppose our stopping rule kicks in, we exit, we've converged. Now we have wound up here with three very distinct and fairly well-fitting clusters in terms of their centroids. There is the final green cluster. Here is the final blue cluster. And here is the final red cluster. And again, within each cluster, we can compute the error metric, right? We could take each data point, measure how far each data point is from the center, right? That gives us a distance metric, and look at the average of the sum, some weighted average. And that gives us an error. And I would argue that this orientation of the clusters, of the centers here, minimizes the weighted average error metric that we would look at across the clusters. So that is how the K and X means cluster algorithms work for a for a given K. If you were doing this for X means clusters, you would do this for first with one cluster, then with two, and then with three, then with four, so on and so forth, until you found the one that you could validate as giving you really the lowest error within the clusters. So you're fitting not just K clusters to the data, or assigning rather the data to K clusters, but you would really be looking for what is the right amount of clusters at the same time you're solving that problem. Okay, so you would loop that over that value K. You would loop this process over that. Let's real quick wrap up with a quick discussion of hierarchical clustering. So the output from hierarchical clustering can also have a dendrogram interpretation, very similar to CART in only that regard, really. It is a purely unsupervised technique. And there are two types of hierarchical clusterings. There is a type known as divisive hierarchical clustering, which is top-down. The way that works is it puts everything in one cluster to start, and then it breaks those clusters up into smaller and smaller and smaller clusters. The other is known as an agglomerative technique, and this technique is a bottom-up technique. It assigns everything to its own cluster. Each observation gets put in its own cluster, and then it starts combining observations together. So this picture on the right, I'm going to show you in a minute, is a representation really of an agglomerative technique, but it's flipped upside down here. We started with A, B, C, D, E, and F as observations in their own separate classes, and then we started to combine them throughout the iterative process. So it's a real quick look at CART, random forest, and some clustering. Stay tuned. I will implement some of these in a software package for you.